Welcome all to Facilities Planning and Logistics course. So we continue our discussion on facility location problems. In our previous lecture, we talked about mini-sum location problems on continuous plane with rectilinear distances, and also we learned how to sketch isocost contour lines for these problems. And at the end of the previous lecture, we also started learning about minimax problems with rectilinear distance on continuous plane. And in this lecture, we will be solving some examples for this problem. So let's remember what was this problem. Actually, especially in the case of if you want to locate a facility, an emergency facility, so that you want to minimize your reaching time to an emergency situation, then the minimax objective is more meaningful. And the objective can be stated like this, in which we try to minimize the maximum rectilinear distance. So this inside term is actually your rectilinear distance, and this GI, we said that it is sometimes in some problems we may need it. It is some kind of a fixed travel associated with all existing facilities. I mean, it's always there. Whatever your X and Y coordinates, it can be the case. For example, in a multi-store location problem, the elevator, the length of the elevator, you should always cover that distance. So it is some kind of a fixed travel distance. In some cases, you don't have it. It is zero. But in some problems, you may have it. And as you can see in this problem, in this example, there are no weights, or all the weights are 1. So the solution, of course, if there are weights, still it's a valid problem. It's a real problem. But with those weights, the solution procedure that we will be learning is not possible. You can't use this solution procedure with the weights. You can use it only if the weights are all equal. Okay, so therefore be aware of this situation. And how do we minimize this maximum solution? We simply compute or calculate 5 different values related to or using the X and Y coordinates of the existing facilities and the fixed travel associated with each facility. So AI is the X coordinate of the ith facility, and BI is the Y coordinate of the ith existing facility, and GI is the fixed travel associated with this existing facility. And we simply calculate the minimum of these values over all I, over all existing facilities. Okay, so also this one, C2, it is the maximum of these values over all existing facilities. So you may say that where did these values came from? How did we obtain this? Actually, it is coming from this objective function. So look, this is a minimization, minimize max, min max type objective function, which includes absolute values in it, and X and Y are decision variables. So it is not a linear function. In order to solve it using an LP solver, you first need to linearize it. And when you linearize it, this function, you would be seeing where these AI and BI values are coming. Okay, it is from there. So we didn't prove how we obtain these values. It is not the focus of this course, but we will learn how to solve such problems. Okay, so C1, C2, C3, C4 are quite similar to each other, but we have, let's say, plus and minus signs. They are different for AI and BI values. But if you look at C5, C5 is somehow different than the former ones, because it is calculated as C2 minus C1 the maximum of C2 minus C1 and C4 minus C3. And with an example, when we do an example, you will understand exactly what's going on. The optimal solution, optimal objective function value here will be found by dividing or taking 1/2 of this C5. So it is, you don't need to solve anything. You just calculate these values and take 1/2 and it's your objective function. It is the minimum value of the maximum distances. And you will be knowing the optimal x and y coordinates, again calculated using these C1 up to C4 values. So okay, then how we will find the optimal coordinates? By using these two formulas. Okay, so it means that actually if you look at this one, in this problem there seems to be two optimal solutions. One is x1, y1, we represent it by this, and we calculate it as the 1/2 of C1 minus C3 and C1 plus C3 plus C5. Okay, what is this? It's actually this. So this part is the x coordinate, so it is x1 star, and this one is y1 star. But of course, this 1/2, it means that we are taking half of this and half of this. And similarly, for the second alternative solution, this 1/2, it means that x is equal to C2 minus C4 divided by 2, and y is the second component divided by 2. And as I told you, the optimum objective function value is calculated as 1/2 of C5. Again, I'm sure it is still not clear how do we do this, but with the next example, with the following example, it will be much more clear. Let's consider this example. It says that there's a portable emergency first aid station which is to be located inside a factory. The maximum travel distance, so this criteria says that we are interested in the maximum distance by any worker to the station has to be minimum. So we try to minimize the maximum distance. So we learn that the objective function is min-max from this statement. Due to many safety and hazards within the factory, travel follows rectilinear distances. Okay, rectilinear distance, we learn it from here. It says that there are 30 existing workstations within the factory where the XY coordinates are given in the table in the next slide. Okay, the fixed travel for each workstation is assumed to be negligible. So GI values from this statement, we understand that GI is equal to 0 for all I. There is no such fixed travel. It says it's negligible. Are on the same floor and have small area compared to rectilinear distances. And the question is, where should the portable emergency first aid station should be located? Okay, this is the min-max rectilinear distance continuous facility location problem. And we will implement the formulas that we learned to solve this question. And let's implement it. Let's use those formulas. Okay, so this is the problem data still. We are said that there are 30 existing workstations. So first workstation, second workstation up to 15, 16, 17, up to 30. And these are the x coordinates of the stations and these are the y coordinates of the stations. And we need to calculate or we need to find the xy coordinate of the existing facility. And remember our procedure. So we will follow this procedure. Let me give the procedure as step by step. So it says that first calculate AI plus BI and minus AI plus BI for all existing workstations. Okay, so let's say if a workstation is in coordinate 2, 3, what do? We first calculate AI plus BI, which is 5. This is AI plus BI. And then we calculate minus AI plus BI. So minus 2 plus 3, it will be 1. Okay. So this is for let's say P1. Then for P2, we do the same thing. So in our question, we have 30 facilities, and for all 30, we need to calculate these two values. Then this procedure differentiates whether, depending on you have a GI value, the fixed level, or not. If you have a fixed level, then you go into step 2, otherwise you go into step 3. So if GI is not equal, then what do? We add and subtract GI from the values found in step 1. So for this one, we calculated, let's say this to be 5, and assume that GI value is equal to 1. What do? We add it to this one to obtain 6, and we subtract it from this one to obtain 4. So we will have two separate values. Otherwise, if GI is equal to 0, what do? We find the minimum and maximum for all values from step 1 and calculate C1, C2, C5. If GI is not equal to 0, then we find the minimum and maximum for all values from this step 2. So the minimum and maximum values of all these calculations. Okay, again, I can understand that by just reading this procedure, it is not still very clear. But again, in the next slide, I will be implementing these steps on our example problem. And at the end, we calculate x1 star, y1 star, and x2 star, y2 star by using the values of C1 up to C5 that we calculated with this procedure. Let's apply these steps to our example problem. So step 1. Now I have listed all these facilities 1 up to 30 in this table. Their x coordinates and their y coordinates are listed. Then in step 1, what we need to do? We need to calculate AI plus BI. So let me show it here. For the first facility, AI plus BI is 20. And minus AI plus BI is 0. Okay, so the order is important. AI is negative, BI is positive. So for the second one, it is 55 minus 10 plus 45. This one is 35. The next one, their summation 160, their difference 130. And you need to do this for all 30 of them. This is the first step. Okay, so let me show these calculations, the results. And yes, these are the results of AI plus BI and minus AI plus BI. So I repeat it for all stations, for all existing facilities. Next step, since in this example GI is 0, I'm not adding and subtracting these GI values from here. Otherwise, if GI was not 0, for each one of them, for each one of these, I should add GI and subtract GI. To this one, add GI and subtract GI. So actually the number of values would be doubled. Here we calculated AI plus BI for 30 facilities, this one for 30 facilities. Then actually what we do, we need to calculate it 30, 30, 30, and 30 in total. So instead of 60 calculations, we will be making 120 calculations. Okay? So let's continue. After calculating these values, the next step, we move into step 3, in which we need to calculate C1 up to C5. Okay, so C1, what was it? It was the minimum of AI plus BI. Okay, the minimum of AI plus BI. So what do? I look at this column here and here. There are 30 facilities. Look at here and find the minimum of them. And the minimum appears to be 20, this one. Okay, so C1 is 20. Next, I need to find C2. C2 is the maximum of these AI plus BI values. So look at them. Find the maximum. I see 220, 270, 310, 325, 370, and as you can see, the maximum is this one. Actually, in this example, the minimum appeared to be the first one and the maximum appeared to be the last one. It is not necessarily valid. In a question, the minimum can be at anywhere and the maximum can be anywhere. So don't just take the first one as minimum and the last one as maximum. Okay, find the minimum and maximum of these values, and they will be C1 and C2. And okay, C1 and C2 are related to AI plus BI, and C3 and C4 are related to next column minus AI plus BI, and I need to find the minimum and maximum of them. So minimum of this column, look, 0. Okay, negative 30, there are some negative elements. So I'm going to find the minimum. Okay, pay attention to the sign. So minus 30 is less than minus 25. Minus 55 is less than minus 25. So find the minimum, and the minimum appears to be negative 175. And similarly, for the second column, find the maximum. Okay, find the maximum of all these, and as you can see, the maximum is 150. Then, after calculating these min and max values as C1, C2, C3, C4, the formula for C5 is this. Maximum of, let me write for our example, it will be maximum of C2 minus C1. So what is C2? 395 minus what is C1? 20. Okay, and the next one, 150 minus C3. And what is C3? It is minus 175. Pay attention to the sign. Okay, so I have written it under parentheses. And using these, we need to calculate the C5 value. Let me clean up here and it will be clear. So the maximum of 375 and 325, and their maximum is 375. So maximum is this. And actually at this point, we immediately know that our optimal objective function value is equal to 375 by 2. This is the optimal objective function value. But the question, what is the optimal coordinate? What are the optimal x and y coordinates? Then I need to use again this x1, y1 and x2, y2 formulas to obtain those coordinates. And when we implement these formulas, okay, remember x1 star is c1 minus c3 multiplied by 1 over 2. And it makes 97.5, and y1 is c1 plus c3 plus c5 divided by 2, which makes 110. Similarly, x2, y2 are 1/2 of these two values. Just use the c1, c2, c3, c4 values that you find in the previous step in these formulas to obtain these two coordinates. Now we obtain these two coordinates. The first one is this. Where does it in the coordinate system? Look, this coordinate is, let me see, 97.5 and 110. Okay, this coordinate. And this coordinate is 122.5 and 85. If you look at this. Then the optimal facility or the facility can be located on anywhere on this line segment. Anywhere. These are alternative optima. And they will provide you the same objective function value. It means that there are infinitely many solutions to this problem, but the idea is to find this optimal coordinate. Okay, now you can ask this question. After finding these two values, these two coordinates, we know that the optimal location of the facility will be on the line segment connecting these 2 points. But mathematically, how can we represent those points? And actually, if you remember your LP course, we already represented such alternative solutions in a similar way. We can do this. We can say the optimal coordinate will be, let's say, lambda times 97.5 and 110 plus 1 minus lambda times 122.5 and 85. Okay, but what is lambda? Lambda is just a parameter and it can be selected in this region between 0 and 1. So for any selection of lambda, you will obtain a different point on this plane. You can select lambda to be 0, you can select lambda to be 1, you can select it to be 0.5, 0.7, 0.8, whatever, and it will give you one of the points on this one, on this line segment. So this is the mathematical representation. In a more general way, I can write it if the first one is a, let's say, a 1 star, this is x1 star and this is y1 star and this is x2 star and this is y2 star, then the optimal coordinate will be lambda times x1 star and y1 star plus 1 minus lambda times x2 star plus y2 star. So in a coordinate system, if you want to represent a line segment between 2 points, you can represent it in this way, in this format. Okay, so this is the end of the solution, and we know that the optimal objective function value is 1/2 of the C5 value. And look, where is the optimal objective function value in this question? So if you look at this line segment, remember again, we want to minimize the maximum distance of the new facility to the existing facilities. And we are dealing with rectilinear facilities. Assume that we decided this end of the line segment to be our optimal location. So we located our facility here. Then, in order to find which existing facility defines your objective function, you should calculate the distance of the existing facilities to this one. For example, the distance of this existing facility to the new facility, which is the red dot, the rectilinear distance, you can measure it like this. By the way, remember, don't be confused. Measuring the rectilinear distance in this way and in this way are identical because their total length is identical. You are covering this length, which is equal to this one, plus this length, which is equal to this one. And actually, if you want to go from this facility to here in this way, again, this is also rectilinear distance because look, this plus this equals to this total length, and this plus this equals to this total length. So you can go in any one of these ways in rectilinear distance, and it will be your distance. And as you can easily observe, this one is very close to the new facility, and the maximum distance will not be that one. Most probably the maximum distance will be in one of the far away corners. And if you look, the rectilinear distance of this one to the new facility is this much, or this one is this much. So one of these will be giving your objective function value, the maximum distance. So I want to solve another example here, okay? And in this example, we will have 8 facilities. So let me list the facilities here. PI, their AI, and BI values. These are the problem input, remember. So I have 1, 2, 3, 4, 5, 6, 7, and 8 facilities. and their x and y coordinates. The first one is in coordinate 0, 0. The second one 4, 6. The third one 8 and 2. Fourth one 10 and 4. 4 and 8. Okay, 2 and 4. 6 and 4 and 8 and 8. This is the problem data. Now our solution procedure starts from here. And what do we need to do? We need to calculate AI plus BI. Again, in this example, GI is 0. Okay, so actually let's change the problem. Let's assume that GI is not 0 and assume that GI is equal to something, I don't know, 2. It is given as 2. So what do we do? The first thing is AI plus BI minus GI, and then I will calculate AI plus BI plus GI, and then minus AI plus BI minus GI, and minus AI plus BI plus GI. Okay, these 4 columns I need to calculate. The first one, 0 plus 0 minus 2, it is minus 2. 0, 0 plus 2, it is 2. Okay, minus 0 minus GI, it is negative 2, and this is positive 2. The second one, 10 minus 2, 8, and 10 plus 2, 12. 2 minus 2, 0, 2 plus 2, 4. Okay, next one, again 8 plus 2, 10, 10 minus 2, 8, 10 plus 2, 12. So minus 8 plus 2, it is negative 6. Negative 6 minus 2, negative 8. Negative 6 plus 2, negative 4. Next one, so 14 minus 2, 12. 14 plus 2, 16. And then minus 6 minus 2, minus 8. Minus 6 plus 2, minus 4. Okay, this one, 12 plus 2, 12 minus 2, 10. And 12 plus 2, 14. And this one, 4 minus 2, 2. And 4 plus 2, 6. Next one, okay, 6 minus 2, 4. And 6 plus 2, 8. And 2 minus 2, 0, and 2 plus 2, 4. Next one, 10 minus 2, 8, 10 plus 2, 12, and minus 2, minus 2, minus 4, minus 2 plus 2, 0. And the last one, 16 minus 2, 14, and 16 plus 2, 18. And for this one, it is 0 minus 2 minus 2, and 0 plus 2, it is 2. So I have calculated all these values. Now I need to find the C1 value. C1 will be the minimum of these values. Okay, so which one is the minimum? Just look at here, and I see a negative 2. Okay, so C1 is equal to minus 2. C2 will be related to this column, and it will be the maximum of these. And if you look at this, I see the maximum as 18 here. So C2 is 18. And then C3 will be the minimum of these values. And I see that minus 8, this one or this one same. Minus 8 is the value of C3. And C4 is the maximum associated with this column. And I see that the maximum here is 6. Okay, so after calculating these C1, C2, C3, let's calculate C5, which will be the maximum of C2 minus C1 and C4 minus C3. And actually it will be maximum of C2 is equal to 18 minus C1 is equal to minus 2. And the next one, C4, which is 6, minus minus 8. Okay, so we have maximum of 18 plus 2, 20, 6 plus 8, 14, and this maximum is 20. Okay, then the optimal objective function value is 1/2 of it, which will be 10. Okay, so we calculated just the objective function value. Now we need to calculate x1 star and y1 star. X1 star and y1 star, the first coordinate. And the formula for this one, it is 0.5 times C1 minus C3 and C1 plus C3 plus C5. Okay, so 0.5 times C1 minus C3, C1 is minus 2 minus C3 minus 8. So pay attention to signs. And the second one, minus 2 plus 8 plus C5 is 20. Okay, so from this first part, 8 minus 2, I obtain 6. And from this second part, I obtain 26. And I need to take 1/2 of these values. So the first coordinate will be 3 and 13. Okay, this is the x and y coordinates of the first one end of the line segment. The second end, I need to calculate it as x2, y2 star, which will be 0.5 times C2 minus C4. Okay, just the application of these formulas. And don't worry about memorizing these formulas. They will be provided. Okay, so C5, remember, C5 value is 20. 1/2 of C5 is equal to your objective function. So this 10 is not C5. It is your optimal objective function. The value of C5 is 20. Okay, so for the next one, C2. What is C2? It is 18 minus, what is C4? 6. And what is C2? It is 18 plus C4, 6 minus C5, 20. And I will be taking 1/2 of it. So the first one, 12 by 2, it is 6. And the second one, 24 minus 24, 4 by 2, it is 2. So the coordinates of the new facility will be on the line segment that connect these two. And if I sketch just a small sketch here of x and y coordinates to present you. So let's say this is 3 and this is 13. So the first coordinate is 3 and 13. And the second coordinate is, let's say, 6 and 2, somewhere here. And the optimal facility will be on this line segment. Okay, so this is how we obtain the optimal solution to this problem.